Right, oxidation numbers or oxidation states. And I think we just need to go through a lot of rules that you just have to learn. And the first thing that I would write down is elementary form. What do I mean with that? On its own. That's what I call it. On its own. Elementary form, oxidation number is always 0. For example, N2. It's only nitrogen. Helium. Phosphorus. Bromine. Sodium. On its own, oxidation state is 0. Yeah? With a posh word, we can call this elementary form. The second thing that you can look at is the groups. Group 1 always +1. And now it's not on its own anymore, right? So this is the only one where it's on its own. So group 1 will always be +1. So if I take sodium chloride, the sodium will be +1. Group 2 always +2. If I go for barium chloride, barium will be 2+. Group 3 always +3. Aluminium chloride, aluminium will be 3+. What we need to keep in mind is that the whole sodium chloride, the barium chloride and the aluminium chloride, of course, will be neutral. Therefore, in all three cases, the chloride will be 1-. And I will come back to those in a moment. Group 4 is a mess. Group 5 can be plus or minus. Group 6 can be a mess. And group 7 can be a mess. And group 0, or better known as group 8, even noble gases can make compounds, especially argon and krypton, krypton and xenon. But we will deal with that. Now, the best tool to start with is oxygen. Oxygen is always -2, except in F2O, where it will be +2, and in hydrogen peroxide, where it will be -1. Another good one is hydrogen. Always +1, except with a metal. Where it's -1. group 7 with a metal -1, with a non-metal positive. But we don't know by how much. It could be 1, 3, 5 or 7. And these are the basic rules. You need to learn them. And the good thing is that most compounds will have oxygen in there. So oxygen will be a good starting point. So what I'm going to do now, I'm going through several examples and see how we can solve this. And then eventually I will give you a handout. So take this over. It's a good tool to start with. And then I quickly wipe it out and I will write down some examples. For those people who are already finished and want to have a puzzle, let's start with I want the oxidation states for the potassium, the chromium and the oxygen. And oxidation states are quoted per atom. So to give you some advice, you start here with either the oxygen or the potassium, and then you can solve the chromium. And I will just go through this example. Potassium is group 1. Therefore potassium can only be 1 plus. Oxygen is per definition 2 minus. It is not an exception that we're dealing with, so oxygen is 2 minus. What is the chromium? We know that the whole compound will be neutral. So what I've got here is 2 potassiums, that is 2 plus. I have 7 oxygens, that is 14 minus or minus 14. So what is the value, the oxidation states, of the 2 chromiums? Well, if the whole compound is neutral, the 2 chromiums need to be 12 plus. Therefore, because we've got 2 chromiums, each chromium will be 6 plus. Now I'm starting with quite a difficult example, because this is the first thing that came to my mind. Sodium, hydrogen, phosphate. Well, sodium is group 1. So the oxidation state of the sodium will be plus. Yeah, 1 plus. Hydrogen is always plus except with a metal. Although it is with a metal here, it is exclusively with a metal. So in other words, hydrogen here will be plus. Oxygen, it's not an exception, so oxygen will be 2 minus. What will be the oxidation state of the phosphorus? Well, we got 1 sodium, which is plus. We got 2 hydrogens, each of them are plus, so that is 2 plus. We got 4 times 2 minus, it's minus 8. Therefore, the oxidation state of the phosphorus will be 5 plus. If you're just wondering why we need oxidation states, well, we use them for so many things, especially redox reactions. This comes back in A2, and I would just say, learn the rules. Let's take another one. Cl2O7. We stick to the rules, and we notice that this is not an exception for the oxygen. So the oxygen, again, is 2 minus. The halogen, the chlorine, is not with a metal. Therefore, it will have a positive oxidation state. Well, 7 times 2 minus is 14 minus. Therefore, if the whole thing is neutral, the chlorines should be plus 14. I've got 2 chlorines, therefore each chlorine will be 7 plus. Because plus 14 and minus 14 overall will give you 0. We can make things a little bit more difficult, and I'm going back to the example there of what is happening. And I'm just going to the phosphate group on its own. Yeah, this is the phosphate group. It's an N-ion, and it has an overall negative charge of 3 minus. Let's stick to the rules. Oxygen is 2 minus. I've got 4 oxygens, therefore that will be 8 minus in total. Now if the phosphorus was 8 plus, the overall charge would have been 0. But the number, the oxidation state that I'm looking for the phosphorus, plus the oxygen, needs to be 3 minus. So therefore, the phosphorus will be 5 plus. Let's take another anion, the sulfate anion. SO4, 2 minus. Again, it has an oxygen, therefore oxygen will be 2 minus. We have 4 oxygens, that is 8 minus. The whole thing is 2 minus, therefore the sulfur has to be 6 plus. And sulfur, for instance, can have different oxidation states. Let's just go through some of the sulfur compounds. H2s, the smell of rotten eggs. You can have SO2. You can have SO3. You can have SO4 2 minus. You can have S2O3 2 minus. Stick to the rules. Hydrogen is always plus, except when it's with a metal. Well, sulfur is not a metal, So the hydrogen is plus, you got 2 of them, so the sulfur here is 2 minus. In the next example, oxygen is 2 minus, you got 2 of them, so the sulfur will be 4 plus. With the sulfur trioxide, again, 1 oxygen will be 2 minus, you got 3 of them, the whole thing is neutral, so the sulfur will be 6 plus. We've already done this one, oxygen 2 minus, sulfur 6 plus. So what is happening here? Again, oxygen is 2 minus. That will give you an overall charge of 6 minus. The whole thing is 2 minus, so each sulfur will be 2 plus. Now an interesting one with sulfur, because it's a good example. S4O6 2 minus. Oxygen again is 2 minus. We got 6 of them, so that is 12 minus. The whole thing is 2 minus, so the 4 sulfurs need to be 10 plus. But now we got a problem. How can I divide 10 over 4 sulfurs? Because 10 divided by 4 will give an oxidation state of 2.5. You cannot have an oxidation state of 2.5. So how can we divide 10 plus over 4 sulfurs? I will go into another example in a moment. So pretend you got 4 sulfurs and you have to hand out 10 pounds to the 4 sulfurs. How would you do that? Well, you give 1 sulfur 3 pounds. You give another sulfur 3 pounds. And then the last remaining one, well, you can only give them 2 pounds each. So 2 of the sulfurs will have an oxidation state of 3 plus, and the other 2 sulfurs will have an oxidation state of 2 plus.
Where'd you write that down? Do you have to write that down?
You would write that down, literally. That's a very good question. You would write that down. I would do that in Roman numerals. And then just the other way around. So, much better to do it that way. And I will come back to Roman numerals in a moment. And there are examples enough like this, because I can write down one of the iron oxides. Yeah, the whole thing is neutral. Oxygen again is 2 minus. That will give you 8 minus. Therefore, the 3 ions need to be 8 plus. Now, how can I do that? Well, it's literally going to mean I've got 3 ions. How can I divide that reasonably fair? 3 plus, 3 plus, 2 plus. Yeah, and what you want to do is you want to divide it as fair as possible. What you could have done with the sulfurs was 4, 4, 1, 1. But that's not really fair, is it? It's fairer to do 3, 3, 2, 2. Now, we have a special notation that you need to know, and this is something that students always seem to have problems with, and it is the use of Roman numerals. Now, I always like to say that I would be a brilliant Roman, because I really like the Romans, but you will have some problems with the Roman. Because Romans didn't know anything about the number 0, and Romans didn't know anything about negative numbers. So the only thing they know is 1, 2, 3, 4, 5, 6, 7, and that's as far as I'm going. So how would I write down that iron oxide? I can call it iron oxide. But there are so many iron oxides. You know, let's write down an iron oxide, FeO. Fe2O3. Fe3O4. They're all called iron oxide. How do I know which one is which if I'm not going to use a molecular formula? So I need to introduce Roman numerals. So in other words, this is going to be called iron Roman numeral 2 oxide. What does the Roman numeral mean? The oxidation state of the iron is 2+. What am I going to do with the next one? Well, it's again iron oxide. Roman numeral 3, because this will be 3+, oxide. So the oxidation state of the iron will be 3+. So what am I doing in the last one? We just solved it over there. I call it iron Roman numeral 2, 3 oxide.